Hey everybody, and welcome back to Linear Algebra Online. Today we're going to just talk about proof by contradiction, which is a really famous proof technique, and the idea is right here. So there's some things in the world, like this is a classic example, and I'm kind of excited because I've actually never taught this problem, but this is like a super famous problem that every math person knows, and it's really exciting that I get to teach this today. But basically, there's some things like this, where if you just thought, okay, I'm going to try to prove that root 2 is irrational directly, you literally probably just hit a wall right off the bat. It's just too hard to try and prove some simple things like this directly. So this is a classic contradiction proof. And basically the idea is that we're going to assume the conclusion is false, okay? And we're going to arise at some sort of contradiction. So for this example, we're going to assume that root 2 is rational, and then we're going to arise at some sort of contradiction. And again, I would always recommend you try and do these on your own, and then, like pause the video and think about it. I'm just going to jump into it right now, but this is a very, good problem, and I think a lot of you could probably solve this without me just walking you through it. So I would definitely recommend you stop and think about, if we assume it's rational, and see if you can rise at some contradiction, which would then imply that what we assumed must be wrong, and so therefore the conclusion is true. But this is how you do it. Okay, so we're going to assume. Okay, ready? I don't like that color. Let's do green. We're going to assume that root 2 is rational. So root 2 equals like a over b for some ab in z. Right? It's just like the definition of rational. We're going to also add the part that we're going to also assume that a over b is fully reduced. And this just makes the argument easier. Basically a and b can't both be even. Okay? So now I'm just going to do a little bit of math. Okay, so if root 2 equals a over b, this would imply that 2 equals a squared over b squared, which would imply that 2b squared equals a squared. Okay? This means that a squared is even, right? Just because it's 2 times some integer, so that means it's even, right? And then we're going to use this to kind of get to our contradiction here. So I guess we should also add, since a squared is even, we also know that a is even. Oops, I want to delete that. A is even. And we know this just because that's how numbers work. If you have an even number, you square it, it's even still, right? 4 times 4 is going to be even. And that's just kind of like a basic property of numbers that we can take for its truth, right? And so I'm going to let a equal 2c for some c in z. That's just because a is even, so it's got to equal 2 times something, okay? Now substitute. We're going to go back to that red line and specifically the n part. We're going to say 2b squared, which equals a squared, would then be equivalent to 2b squared equals 4c squared, which would then be equivalent to, just if I divide about by the 2, b squared equals 2c squared. So this means that b squared is even, right? Also, I guess I can add b is even. And then this is the important contradiction part. If, I don't know why my eye is not working here. I'll try this again. If A and B are even, then root 2, which equals A over B, can be reduced. And we assumed otherwise, so we have a contradiction. And a lot of times we do this double arrow, like one point at each other, because it's kind of like some sort of issue there. And I don't really have room, but the last line I would write is basically just kind of summing it all up. So, I don't know, can I write it? I guess I can. So, therefore, what we assumed is wrong, and thus root 2 is, oh no, irrational. I'm running out of room. Irrational. Oh no. You can read it, I think. Irrational. Okay. I'm out of room there. But the idea is, assume that the thing you want to show is false. Okay, so root 2 in this case being rational. And then that means it has a structure here of a fraction. And then we showed that fraction would basically, we're assuming it's like not reducible. And so we get this weird contradiction where it basically would be reducible. So you would get that a squared and b squared, or a and b, are both, they're both even. And so that's an issue. You wouldn't be able to get that if it was rational. So what we assumed, it being rational, is wrong, and thus it must be irrational. So that's a really famous proof. Probably the most famous proof by contradiction is this one, though. And this thing got proven way back in like 300 BC, and it's very straightforward, I think, and is another good example to kind of understand how proof by contradiction works. So this is Euclid's proof of basically the infinity of primes, which to this day is still basically how we teach this. There's not just one way to prove something, definitely, but people still agree that this is like the cleanest, nicest way to do this, okay? So for this problem, we're going to do a proof by contradiction. So we are going to assume that there exists a finite number of primes. So we can list them. Basically, P1 will say P2 Pn, because it's finite, it just ends at some number, n, period. And we're going to consider the number, what am I going to call it? I don't know, A, which equals that list of primes, not listed, multiplied. So P1 times P2 times blah, 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 P3, so on up to Pn. All of that stuff plus 1, okay? All we're doing is assuming here that numbers are infinite, but that's like one of those basic axioms that we can take for granted. And I'm going to say we know all numbers greater than 1 have at least one prime divisor, which is another thing that we there are proofs of this kind of thing, but it's another just kind of basic number theory idea that we know, like things like 12, which is like 3 times 4. 3 is a prime divisor of that. And I'm going to call it P sub k. Oops, let's do. Okay, so now we know that P sub k basically divides A. I'm just going to say something like, since P sub k divides A, by definition, we have that P1, P2, ... this product of primes, and then we've got somewhere in there pk minus 1, pk plus 1, ... pn, right? Because it's pk is some prime divisor. So in my product of primes that I made up, it's in there, right? So that thing plus 1, which is my A, right? All of this is just A, right? That thing has to equal like CPK for some C in Z. That's because of the definition of divides. Now, if you just divide, you have like a PK on both sides. I'm going to say something like, therefore, 3 dots like in a little triangle like this is therefore. Therefore, we know that P1, P2, blah, 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 multiplied together. Maybe we'll drop the PK ... Pn. Never mind, that's fine. So this thing plus 1 over pk, that's what I'm dividing by, would equal c. Okay. So we could rearrange the thing. So c could equal, nope, that's not what I want to do. So we want 1 over p sub k to equal c minus P1, P2, ... pk minus 1, pk plus 1, ... pm. So this thing. So that's what 1 over pk equals. But this is a contradiction. And I would encourage you to pause and think about why it's a contradiction. And I'm going to write right now why it is. But the idea is the kind of structure of the number. So this thing is rational, and this thing is an integer, and those can't be equal. Again, I've ran out of room, which is unfortunate, but proofs sometimes take a little while. But the idea is we've come up with following the assumption that there's a finite number of primes, we get that a rational number basically equals a integer, but we know that can't happen. So we would say something like, since a rational number cannot equal an integer, then what we assumed is wrong, and therefore there is an infinity of primes, not a finite number of primes. So again, minus some extra stuff here, but basically just the conclusion part, elaborating on this piece. We'd be done there. And that's like how we still teach students that there's an infinite amount of primes. We don't know all the primes, and there's a whole bunch of weird things out there where we don't even know how to find all the primes, and we know we're missing some of the primes between the ones we know, but we know that we can keep finding them. It's actually a big problem in computer science right now because of something called RSA encryption, which is still a really safe way that we secure all sorts of things like bank transfers and stuff like that. But if we can find a bigger and bigger prime, we actually can make things a lot more secure. It's a big problem right now, still in math. But that's how you do a proof by contradiction with the famous proof of an infinity of primes. So I just really quick want to say when we would kind of use these things and just kind of what we're doing, I guess, summarizing that with some symbols and that sort of thing. So it is very useful for a whole class of proofs of the form, there exists a unique, ... So there's a whole bunch of things in math called there's like these uniqueness theorems. So in like differential equations, actually, we didn't really prove any of these last year, but there's a whole bunch of things that say there exists a solution to this differential equation and it's unique, meaning it's the only one. But if you have, if you can use proof by contradiction, basically the idea is that you assume that there exists another solution of that form, and then you show some sort of issue with assuming there's, like, in a sense, two solutions. It's a very common trick with anything that starts off with there exists a unique. So we will see some of that, like ideas this year where it's like, show that there exists a unique inverse to the matrix, blah, blah, blah. And a good way to maybe tackle that is to use a proof by contradiction and assume that there exists like a second inverse or something and show like the issue that arises with that. So the idea of what we just did is summed up right here, straight out of the book for the proofs that we're using. But if we want to show if P then Q for contradiction, we just suppose P still holds, but then that not Q is happening. And the idea is that we should arise at something that says like C and not C, which is like the idea that there's something wrong here. So if you're getting like C is even and it's odd, you know that what you started off with right here must be wrong. So then you can say like, well, therefore our assumption that suppose P and not Q is wrong, and thus given P we know Q must happen, or something like that. That's just what we just did. Last thing I will say is that this technique is good and very, very useful for certain things like this. But if you can do a proof directly or with contrapositive, you should do that first. Basically, down the road, if you keep doing proofs and things, your professors are going to start to get more and more picky about like how organized and simple your argument was. And this is the same in like a lot of fields like philosophy and law and things like that. I have a good friend who's a lawyer, and she actually goes into the courtroom and, when she gives her arguments, she needs to go up and give like 10 minutes on like really succinct, clear, to the point, speech on whatever it is. And if she goes up and says the same thing, but in 20 minutes, it is not nearly as effective as saying it in 10. And so if you have like a cleaner, faster way, like whether it's like a direct proof or contrapositive, you should always take those cleaner kind of things. Basically, this term slick shows up a lot when we start getting into proofs. It really is much more of like an art, and it's not as slick to prove something with contradiction that you could just do directly. It sort of adds this negative part right here, and this whole extra weirdness down here adds almost confusion when you could have just supposed P and gotten to Q straight away. So only really use it if you need to.